Okay, I think we are good. Okay, so let us begin. Now, let's turn this on, and we are good to go. All this is set up properly, and there we have it. All right, so today is June 7th, 2016, and today we're going to talk about vectors. Make this big here, and I want to duplicate slideshow set. All right, so the question is, what is a vector? So we want to know what a vector is. So let's look at this, and let's consider this for a moment. So let's consider this. So what is a vector? You've all seen vectors before in various classes, but today we're going to talk about them, sort of build them up from base principles, and talk about exactly what they are. So vectors have two properties. A vector is a quantity with two things. A vector is a quantity with has both a magnitude and a direction. Has both a magnitude and a direction. And a direction. Has both a magnitude and a direction. A scalar quantity has only a magnitude. So we need to talk about what exactly these mean. So a scalar quantity has only magnitude. So what do we mean by this? What do we mean by magnitude? What do we mean by direction? Well, obviously, direction means means an orientation. It means a direction. It means north, south, east, and west. It means some sort of orientation in relation to something else. Orientation in relation to some reference point. In relation to some reference. To some reference. Fundamentally, this is what direction is when we're talking about vectors. And magnitude is the absolute value, or the size, or the magnitude. Size, value, etc. of a vector. So, when we think about this, what are some examples of scalar and vector quantities? Well, example of vector quantities are things like velocity, displacement, acceleration. Oh, what else? We can have electric fields. We can have all sorts of things from electromagnetism. But then, the one we are going to be most concerned about in this class, because of course this is engineering statics, is force. We are most concerned with force. And then with examples of scalar quantities, we can have things like energy. Energy is an example of a scalar quantity. When I say a system has 12 joules of internal energy, I don't say it has 12 joules of internal energy upward. I don't say it has 12 joules of internal energy to the right. I simply say it has 12 joules of internal energy. Energy is a scalar quantity, not a vector quantity. Other examples of scalar quantities, things like distance traveled, speed, etc. So we're talking very general of quantities from physics right now, but vectors again, have magnitude and a direction, so magnitude and direction, while scalars have only magnitude. So in terms of vector algebra, your scalar is simply the magnitude of a vector. In other words, you might say the speed, for instance, is the magnitude of velocity, or if you're familiar from earlier courses from physics, speed, you have heard, would be the absolute value of velocity. Speed would be the absolute value of velocity. So any questions on the distinction between vector and scalar properties? This is fairly straightforward, I hope. It's something you've seen a million times before, but I just want to introduce it fairly briefly. So let's look at this in detail. What do we mean by that? What do we mean by this? Again, make sure, did you all get this? Okay. Let's see. So let's look more about vectors. We're not terribly concerned about scalar quantities in this class. Obviously, this is statics. We're concerned about forces, how they interact, what direction they point, how they balance against each other, that sort of thing. So we're going to be concerned primarily with vectors and primarily with force vectors in this class. In physics, you work with a much greater variety of vectors. Anyone here taking their Physics 2 electromagnetism right now? Anyone? One person? Okay. I know sometimes people take. Their statics. Sometimes people wait to take their electromagnetism till after. But anyway, some people do like getting their physics completely out of the way before moving on to statics. But I think the prerequisite for this is only just the first physics. So anyway, let's look at some quantities of vectors. So let's look at vector properties. Let's see here. No, go back up here. Vector properties. So we know that vectors have both a magnitude and a direction. That is definitional. But what else do we know about vectors? Okay. So let's just discuss a bit about vector properties. Well, first of all, a vector can be moved anywhere along its line of action. Anywhere, and you can read the book to get more deeply into the theory of vectors. We're just going to be talking about the very basics here, but the book will go into it in a much greater and thorough detail. Anywhere along its line of action, especially for force vectors. Line of action. Vectors can be added or subtracted. Vectors can be multiplied, but what we have to do a special kind of multiplication when we talk about the dot product or cross product. Vectors can be multiplied. So these are more the mathematical properties. Vectors can be multiplied through dot or cross products, which we will get to later. Or cross products. And each of these multiplications has their own special implications that we will see. Or cross product. Okay, vector properties here. Now, so let's see, can be added, subtracted, multiplied, etc., etc. Let's see. We also will need to talk about unit vectors. Define unit vectors. Just want to get this down. Unit vectors. A unit vector is a vector of magnitude 1 pointing in the direction of another vector. In the direction of another vector, or just pointing in a certain direction. Your I, J, and K vectors, let me put little hats on those, I hat, J hat, and K hat vectors, these are your Cartesian unit vectors. These are your unit vectors along the x, y, and z axes. Yes, the rectangular ones, exactly, the rectangular ones. And we will see that more going on ahead. So again, vectors have certain properties, namely they can be moved anywhere along their line of action. So we can add them head to, and by addition I mean they can be added head to tail. And we will talk about what exactly these mean. What exactly it means when you add two force vectors together. Well, that doesn't look right. Headed. Head, not headed. Head to tail. Pardon my awful handwriting. Okay, head to tail. All right, so any questions on this basic theory? Okay. So again, what does this mean? So they can be moved anywhere along a vector can be moved anywhere along its line of action. So fundamentally what that means is, consider this bottle, for instance. If I have a force that I apply to the top of this bottle here, it doesn't matter whether I apply it right here, or I could say, for example, I could apply it I could apply a force with my finger to the top of the bottle here, or I could actually use a pen to apply that force a certain distance away. But as long as I apply it along the same line of action, this bottle will behave exactly the same. What I mean by behave, it will exhibit the same tendency to either translate or rotate as it would regardless of where I apply the force. Now, if I apply the force, if I change the direction that I apply the force, or if I change the location that I apply the force, then things can change. But as long as the line of action and the magnitude and the direction of that force that I apply does not change, then the bottle will exhibit the exact same tendency to translate, rotate, deform, etc. So that is just another property of vectors. So everybody got this? Okay. So let's talk a bit about vector addition. What do I mean by vector addition? Let me get this. Vector addition. So we can consider vector addition a variety of ways. We can consider it graphically, where we plot vectors head to tail and find the resultant. Find resultant. That's one way to do it. We can plot them head to tail and find the resultant. So if we have one vector here and one vector here, the resultant is this vector here. So the resultant will be from the tail of the first vector to the head of the last vector. So this would be v1, vector 1, v2, and the resultant. So the resultant would be v1 plus v2. Graphically, it's simply summing up the different vectors from head to tail. So that's one way to do it. Or we can use trigonometry. Trigonometry. You can realize that a triangle will be formed. Can apply properties of triangles. Triangles. Use law of sines, law of cosines, etc. And the book goes into this. So you can use the law of sines, law of cosines, Pythagorean theorem, any convenient triangle properties that you like. You can also use the parallelogram method. And I may have just misspelled parallelogram, but oh well. Don't feel like fixing that. Okay, parallelogram method. What do I mean by this? Well, if I have a vector 1 here, and I have a vector 2 here, well, I could make a parallelogram by plotting another version of vector 2 and another version of vector 1. And the diagonal of this is going to be the resultant. So the diagonal of the parallelogram will be the resultant. Is the resultant. Okay, diagonal of parallelogram is the resultant. So that might be useful to know. And then there are the advantage of that is there are certain special properties relating to the area of parallelograms, especially like when we get to moments and things like that, we'll see. So there can be certain, now they're usually, I just deal with the x and y components. Usually I stick to rectangular form, but there can be times when it's advantageous to use the parallelogram method. I usually don't touch it, but some people really like it, so I did want to mention it here. So, any questions on this basic vector addition theory? Can you all read my squiggly writing there in the back? Okay. All right. Good. Okay. Moving on. Y'all got this? Okay. Now, so I did want to talk a bit more about ways to express vectors. So today I just want to give you a broad overview and sort of a big introduction to everything there is to know about basic vector theory. So ways to represent vectors. To represent vectors. What are the two main ways to represent vectors? Any idea? Exactly, yes. This is fairly straightforward, rectangular and polar. Represent vectors. Now, when we get to three-dimensional, we could talk about cylindrical and spherical coordinates, which you'll see if you haven't already in Calculus 3, I believe. But we're not going to worry too much about that. When we deal with three-dimensional vectors, we're going to stick with purely Cartesian vectors. Purely for simplicity. Now, ways to represent vectors. So there's two main ones, polar. This is represented with a. Actually, let me use a bracket rather than a parentheses. So this is represented with an r and a theta rather than an x and a y. So polar coordinates and polar vectors are represented with an r and a theta. Rectangular are represented with an x and y. Or sometimes they're represented with a, or sometimes something like ai plus b, let's see, or maybe, let's see, maybe a better way to express this would be, maybe just x and y as coordinates, as values. Something like, you can also use unit vector notation where you do something like xi plus yj plus zk, something like that. But anyway, fundamentally what this comes down to for two-dimensional is something like this. If I have my x and my y axis, and I have my r and my theta, I will have x and y components here. X and y. So, what does this mean? How do we convert between these? Now, you've probably all seen this from trigonometry years and years ago, but I'd just like to remind you all how this works, for just as a brief review. Conversions, well, of course, if we want to go from polar to rectangular, we can use the formulas x equals r cosine theta and y equals r sine theta. And opposite, rectangular, to polar, we can use the relationship r squared equals x squared plus y squared, and theta is equal to the inverse tangent of y over x. The inverse tangent of y over x. So hopefully all of that should be fairly familiar. This is actually not even physics, just going back to basic trigonometry. So hopefully that isn't too bad. Any questions about that basic theory of vector representation and conversion? Okay. So ways to represent. So we've gone over ways to represent vectors, ways to convert them, etc., etc., etc. So let's see here. Oh, let's see. What else? So let's talk a bit more about Cartesian vectors. So we're going to be working mainly with Cartesian vectors in this class, so we might mention this a bit more. Cartesian vectors are, of course, your rectangular vectors. Cartesian, rectangular are the same thing. So if you have a variety of vectors, you can actually obviously convert them. Cartesian vectors, I just say, give you another way of adding vectors. So using Cartesian vectors, you can very conveniently do vector addition and very accurately do vector addition. So Cartesian vectors provide reliable and accurate vector addition. Provide reliable and accurate vector addition. In other words, if I have three vectors, if I want to say I have vector A, which is made of components AX, AY, and AZ. And maybe I have vector B, which is made of vector, which is composed of components BX, BY, and BZ. And I have vector C. Oh, let me not forget my little vector signs here. And I have vector C, which has components CX, CY, and CZ. Well then, I can simply say obviously the resultant is A plus B plus C. What does that actually mean? How do I actually do that? I could graph all these and try to do this and try to do it that way. But trying to graph three-dimensional vectors is a very difficult task. Graphing two-dimensional things is inaccurate enough. Trying to accurately graph three-dimensional vectors is a task I don't want to have to do. That's going to be incredibly inaccurate. You're not going to get in. Yes, if we really wanted to do it just to prove a point, we probably could. We could actually create like a 3D-dimensional model, like made of little like sticks positioned at certain angles, and I mean we could do it, but it isn't. But why? It's not going to be very accurate. So instead, for anything three-dimensional, I like to use Cartesian vector addition. So in other words, I am going to say that R is also made of its own x, y, and z components. Rx, Ry, and Rz. And Rx is going to be simply Ax plus Bx, oh, that's a plus sign, plus Cx. Ry is going to be Ay plus By plus Cy, and Rz is going to be equal to Az plus, oh, I forgot my Y there, plus Bz plus Cz, like so. Okay, and that is how you can find the overall components of this. But now, what if I want to get what if I want to go and get the magnitude of R? Well, if I want to get the magnitude of R, I simply apply the Pythagorean theorem for 3 dimensions, and I get R is equal to the square root of Rx squared plus Ry squared plus Rz squared. Here. All right, so any questions on this? On resolving a force into components, on, I know this is just theory, so I know some of you are probably saying, yeah, yeah, fine, no problem. I mean, but, okay, I've gone over through the equations, and I know some of you are probably just looking at that going, just deer in the headlights, what? And then, although some of you have probably seen this a million times before and are bored out of your mind. So don't worry, we'll go over some examples. I know you like seeing examples, not just equations, so don't worry, we will see some of that. I just need to cover it, but before I can go through examples, I need to go through the wonderful, fun theory of everything. So basically we're building some tools up in our toolkit that we can use later on. So, any questions on this? Okay, so let's go through I think that should about do it for theory, and then on top of that, after that, I just have some example problems that I wish to work through. Okay, so I think we might take a actually very early break today, if that's okay. We got through the theory a bit faster than I'd planned, so we'll take a short break, and then we'll come back and look at some example problems. Okay. Yes. Possible. Yeah, I think so.